All right, so let's go ahead and let's look at an example where we have the volume of a cylinder. So volume equals pi r squared L. So I have a function volume that's a function of two variables, r and L. So I have a tube of circular cross-section, a nominal length of this, a radius of this, determine the uncertainty in the volume. So whenever we're looking at a problem like this, one, it's important to have our fundamental equation. So write out what is our fundamental equation that we're working with here. So that's volume, and then two, what are the variables in this expression? Now, the next step is, do we have bias error or precision error or both? So if I have precision error in some r, some value, some measure n x, that's going to be equal to plus or minus t alpha over 2 nu times s sub x over square root of n. That's going to be my precision error value that I plug in. But nowhere here am I given the number of data points, and that plus or minus is not necessarily the standard deviation. So I don't have the square root of n, so there is no precision error here, or not one that I can figure out. Now, is there bias error in the length? Well, we're not given the tool. So if we're given the tool, we know essentially some of the resolution of the tool, we can estimate that. But we're given a plus or minus value, so my bias error in the length is going to be 0.5 meters. My bias error in my radius is going to be equal to 0.1 meters. So now I can utilize this expression here, where the uncertainty in my volume is going to be equal to square root of partial derivative of volume with respect to my length times my uncertainty in the length, which will effectively just be this value here. Uncertainty. Instead, I shouldn't put BL here, but I was trying to make a point. So we can say the uncertainty in L and the uncertainty in my radius is this squared plus partial derivative of V with respect to R, uncertainty in R squared. So let's go ahead and pull up Mathematica. Mathematica appearing on here. So let's wait. And we can go ahead and look at this. And then now, so I can go ahead and say volume equals pi times r squared times L. And then my uncertainty in the volume is going to be equal to square root of derivative of, or you can even break up into parts. So I could do like dv dl equals derivative of volume with respect to L. dv dr equals derivative of volume with respect to R. And then I could put in the parentheses dv dl, and actually I could do uncertainty in L is equal to 0.5. Uncertainty in R is equal to 0.1. And dv/dl times ul squared plus dv/dr times uncertainty in R squared. And you can see we have these values. So we actually don't. What about R and L? What do we do here? Well, I can actually plug in the nominal value. So uv slash dot r goes to, my radius is 15 meters. Slash dot goes to 15, and then my length goes to 50. So I can just plug in here, and this would be my uncertainty in what units? What are the units here? Basically r to the fourth. Again, so what is the volume here? So r to the fourth. What do we have? What will be my requisite value here once I have my uncertainty? So this is a value here. Actually, we can look at it probably quite a little bit easier here. So dv dl is equal to pi r squared. So that's r squared times another value here, where this is a unit in what? Meters. So meters cubed. So this is my uncertainty in meters cubed here. Now, let's say I didn't want to calculate it in terms of meters cubed. Let's say I wanted to do this in percent. So let's say certainty percent. What I can do is simply divide out by the volume. So vol, my expression. So I can just divide each of those partial derivatives with respect to volume, normalizing by the volume, and I can get this value. I still need to plug in the nominal values here, but we can do this. So I can do, oops. Let's go ahead and plug that in here. So that would be my uncertainty in percent. So let's see if that's true. So I can do volume slash dot, plug in these values here. And then if I multiply this, so that's my total volume. But if I do this, multiply here, then you see the match. So there you go. All right. And you can see that's basically the way that we go through it in our notes. And you can see all those good things. All right. So let's move on to our next example, uniaxial tension.